that is A1
Hi,
as
welcome to
2 times GM1 divided
video
by
on
I5 into lambda 2
two-stage
plus
op-amp
lambda 4.
circuit.
So this is the
So
ultimate
let us
expression
try
what we'll
to
be getting for the first
recap the things what we
stage.
done in the previous
Similarly, for
videos.
the second
So
stage, we
let me
can write it
write
as
the circuit
GM6
diagram of
divided by
two-stage
I6 into
operation
lambda
amplifier.
6 plus lambda 7.
First stage being the
Again, the current
differential
that is flowing
amplifier,
through the
and
second stage is
the second
I6. So that's
stage
why it
being
is I6. And there is no 2 term here
the
because in
CS
the previous
amplifier.
case there
So
was a
both the
term 2,
amplifiers
which is
have
due to the
the
current flowing
active
through
load.
the first stage is
So let us not
half of
write okay what
I5. So
is
that's
the
why
mirror
that 2
circuit
goes
of
to the
those stuff.
numerator. But here in
So
this
now
case,
this is
there is no 2 here. It is GM6 and the current flowing to the second stage, which is I6,
plus
and
minus.
the channel length modulation factor
This
of
is
the
PMOS.
second,
This is also PMOS.
M6 and M7 transistors. These are the equations of
Okay.
gain bandwidth,
This
output
is
pole under
VD
zero
and this
frequencies.
is minus VSS.
And we are supposed to
This is
now
again PMOS
design
transistor.
a
Let us name
two-stage
it
amplifier,
as
meaning
M1,
that in case of design of
M2.
two-stage amplifier, we are
This
supposed to
is
estimate the
M3,
dimensions of
M4.
all the
This is the
MOSFETs
output
along with
voltage.
the value of capacitance Cc.
This is named as M5, and we have the CS amplifier. Okay, now this is again PMOS. This is NMOS. The biasing of this you can consider, okay, it is getting from the same transistor. Let us name it as M6. This is M7. This is a V0 dash. So of course we have assumed that the resistance of the first stage is R1 and the parasitic capacitance is C1. Similarly, looking into this, the resistance is assumed to be so, which will certainly result in V naught by V in magnitude. Suppose if you simply take the magnitude of it, so then this becomes to GM of first stage R1 of first stage multiplied by GM2 of second stage and R out of second stage. This is the gain. If you want to look at where is the pole, there are actually two poles. One is decided by R1C1, other is decided by R2C2. If I write it in the time constant form, it is 1 plus S by omega P1 dash and 1 plus S divided by omega P2 dash where omega P1 dash is given by 1 over R1C1 and omega P2 dash is given by 1 over R2 seat. Suppose if we are writing the pole zero plot, there are no poles in this particular transfer function. So we have there are no zeros in this transfer function. We have two poles. One is at minus omega p1 dash and other is at minus omega p2 dash. So this is the representation of two poles of this transfer function. There are no finite zeros. And if you write the Bode plot of the same, this is omega, this is magnitude, so it has got a constant gain of GM1, R1, GM2, R2 with a frequency of omega P1 dash, then it will have a slope of minus 20 dB per decade, and it is omega P2 dash, then it won't have a slope of this is minus 20 dB per decade. This is minus 40 dB per decade. This is how the magnitude plot of the two-stage amplifier look like. because we found that the phase margin of this must be very less. So in order to improve the phase margin, we will do the compensation. So it is plus compensation. So this is plus compensation. Here the compensation is done using Miller's capacitors. Miller's capacitor is used. So Miller capacitor is that capacitor which is going to have a feedback from output to the intermediate stage. So this is that Miller capacitor. It is 1. CC is the Miller capacitor, which we call it as compensation capacitor. C here stands for compensation capacitor. So in the previous classes, we actually derived the expression for this overall transfer function with this CC in your circuit. So that expression was coming out to be again V naught by V in is equal to, there is no change in the DC gain. DC gain happens to be GM1 R1 GM2 R2 GM1
Yes, sir.
R1 GM2 R2. But what we'll have is we will going to have a location of poles and zeros will be get shifted. And of course, the zero which is there at infinity will be a finite value. So that's what we find in the previous expression. You can see these are the terms. So I will write it as it is 1 minus S into GM2 by CC. So that's what is the location of y. Okay, now y it is this is actually the frequency. Let me write it as CC. Okay, let me write this is 1 minus S into CC by GM2. And the two poles will be shifted. It is now 1 plus 1 minus. The pole position which is there at omega P1 dash will actually move towards the right side. You can see this is moving here, whereas this pole is actually moving to the right side. So because of this compensation capacitor, these poles will going to split away. So this omega P1 dash will go to omega P1, whereas omega P2 dash will go to omega P2, omega P2. Let us, of course, we already saw what is the expression for omega P1 and omega P2. So omega P1. So if you want to write for omega P1, suppose if you write these two equations as it is and then try to see what is the change. You can see here because of this compensation capacitor, this omega P1 dash which is there at 1 over R1 C1, so will now go to this is omega P1. This R1 remains here. Stop this. Delete this. Okay. This is the one which is causing. Okay. Okay, now just a minute. Let me just verify that it's fine. Okay, it's going on. Now you can see this R1 remains same. Instead of this C1, we're going to have it as CC into GM2 R2. So this you can see the denominator has increased, so that this will move towards the right side, whereas omega P2 you can see here this remains as it is, that is C2 remains as it is, whereas R2 will become 1 over GM2. This will actually become 1 over GM2. So this is now GM2 by C2. So this is the expression for omega P1, omega P2. Similarly, we're going to have a 0. So there is a 0 coming into picture, so there was no finite zeros here, so there is a 0 comes here. That 0 is located at gm2 by cc, gm2 by cc. So I can write the expression for this. Now it is uh, s by omega p1 1 plus s by omega p2. Suppose if you want to write only just the now this is we can write what is omega p1, what is omega p2. So the actual expression happens to be gm1 r1 gm2 r2 1 minus s into cc by gm2 divided by 1 plus, because 1 plus s into it is 1 over omega p1, so that happens to be r1 cc gm2 r2 multiplied by 1 plus s into c2 divided by gm c2 by gm2. So this is the magnitude of this is the transfer function. This is the transfer function of the two-stage op-amp after compensation. So we know that this pole will going to move towards left side, this is going to move towards right side, and there is a 0 coming into picture. But typically, how do we understand by circuit analysis why because of placement of this, why the circuit why this particular pole will want to shift? So let us try to observe. Let me write the equivalent circuit of this. So if I write the equivalent circuit of this one, I can write it as something like this. So this is R1, this is the AC equivalent circuit, R1 C1, and I have the second stage. Second stage is connected to this, and then I have the final output voltage. This is R2 C2, and this is GM1 V in, this is GM2 V0 dash, so this is V0 dash, this is V0. Now this is our coupling capacitor, sorry, compensation capacitor CC. This is input voltage, this is input voltage. Now we know that because of using Miller's theorem, I can able to split this coupling capacitor, one onto this side and other one onto this side. I will call this as some Cx, I'll call this as Cy. So what is actually Cx? Cx is actually equal to Cc multiplied by gain of the second stage, whereas Cy is nothing but of course, to be exactly, it is actually Cc into 1 plus AV2, 1 plus magnitude of second stage. How about this Cy? Cy is actually equal to Cc into 1 plus 1 over AV2, 1 over AV2. Because usually AV2 is very large, I can write this capacitance as simply Cc into magnitude of AV2. So this is what is Cx is. What is Cy? Since it is very large, I can write it as Cy is equal to Cc, almost Cc. This is a value. Now if we can carefully observe this, so because we have this Cc capacitance, the image of this Cc capacitance is Cx here, the same is seen on the other side, the same, that is 1 plus 1 over EV seen on the other side. Just have a look at the impact of this CC Miller capacitance on the overall capacitance. Now what is the input capacitance that we are looking now here? Because the capacitance that you are looking now here is, it is this Cx plus C1. So what is the new value of C1, new value of output capacitance of stage 1? Stage 1 output capacitance, it's actually C1 plus of Cx, C1 plus Cx. So as we had this capacitance, it is not only C1 now, it is plus Cc multiplied by AV2 times magnitude. If you can see, the gain of this amplifier is very large, so that this Cc into AV2 is far greater than C1. So after putting this capacitor, the effective capacitance is no more C1, the effective capacitance becomes Cc into gain of second stage. What is actually gain of second stage? The gain of second stage is actually equal to Cc into what is this gain? It is R2 into Gm2. So what is the pole position now? Now pole is due to R1 resistance, and the capacitance is no more C1 as it was in absence of this. Because of this Cc, the capacitance has now increased to Cc into R2 into Gm2. So this is the magnitude by which it has increased. So if you can actually see this here, can you see, is this quantity similar to that of this quantity? Just compare this, just compare these two things. Let me just fold these two and then try to find out what is the value. See now, the capacitance whatever you have here, is, it was actually R1 into C1. So instead of C1 you have Cc is there, then Gm2 R2. So because of this increase in the load capacitance of first stage, because of this Cc, this pole which was there at omega p1 dash has actually moved to omega p1. So that is the reason, okay, why this expression changes from, you can see the earlier expression was only R1 C1 was there. So as I said, so it was R1, this is the modification, this is the change. So it is now changed from C1 to so and so, C1 to Cc into Gm to R2. Gm to R2 is the gain multiplied by the compensation capacitor Cc. Let us see why this particular pole which is there at omega p2 dash will go to omega p2. Why this actually increases? You can see magnitude wise this has reduced. Why this has reduced is, you can see the denominator has increased. So that's why the omega p1 has gone to right side. Whereas in the other case of omega p2 dash, the denominator further decreases, so that's why this increases. Let us see how it decreases. So in this particular case, suppose if you see this coupling capacitor for very high frequencies, if you are looking from here, of course this will going to have, because we know that this is a capacitance, its reactance is, of course, will be less at higher frequencies. So then it will almost look like a short circuit. So at higher frequency, the resistance wise it looks like short circuit. If you have a short circuited drain and gate, we know that the resistance seen from the drain, of course, suppose if I just write this here, suppose if you write it this, now you can see effectively it is short circuited. If you are looking towards this, so earlier what was R2? R2 was given by what? R06 in parallel with R07. This was the resistance. Looking up here was R06, looking down it was R07. So that's why R2 was R06 in parallel with R07. Now when we actually put this capacitance, the resistance looking up here will no more be R06, but if you see this, this is effectively how it looks. So gate gate and drain are shorted. When gate and drain are shorted, we know that the resistance is actually 1 over gm6, 1 over gm6. So what is this 1 over gm6? It is the resistance looking up here in presence of this capacitance. What is the resistance looking down? It is R0 7. So what is the effective resistance now? The effective resistance is R0 7 in parallel with 1 over gm6. 1 over gm6. Why it is 1 over gm6? Because this effectively looks like a short circuit at very high frequencies. So this resistance, which was R2 without this, has now reduced to 1 over gm6 in parallel with R0 7. R0 7. But if you can see, this is a transconductance, 1 over transconductance, and this is resistance. 1 over transconductance is far less compared to R0 7, because this is a transconductance which is in terms of few ohms, whereas this is in terms of hundreds of kilo ohms. When you have few ohms coming in parallel with hundreds of kilo ohms, the effective resistance is almost equal to 1 over gm6. 1 over gm6. This 1 over gm6 is nothing but gm2. This is the effective transconductance of second stage. That's why I can write this R2 as 1 over gm second stage. GM second stage. If we can see omega p2 dash and omega p2, you can see they are same. The capacitance is same. You can see it is C2 C2. It is C2 C2. Instead of this resistance, you have 1 over gm2. 1 over gm2. To be exactly, it is 1 over gm6. Since we are saying that okay, gm6 is the capacitance, sorry, the transconductance of second stage, I am writing it as gm2 here. So this is the reason why this pole, which was there at omega p2 dash without compensation, has moved towards the left side. Why this frequency increases? Means because your resistance reduces. When your resistance reduces in this denominator, naturally omega p2, which is the new pole frequency, will certainly increase. Whereas the opposite was happening in omega p1 dash. Omega p1 dash frequency was actually reducing because your denominator is increasing. Instead of C1, you have Cc into Gm2 R2. So this is the reason why the pole splitting will happen. Pole splitting will happen because of this compensation capacitor, which will increase the load capacitance of first stage, and it will reduce because of increase in the load capacitance of first stage. My omega p1 dash will move towards right side. Since the load resistance of the second stage reduces from R2, of course this was R2, which was R06 in parallel with R07, will reduce to 1 over gm6. So since 1 over gm6 is very small, naturally the frequency associated with will going to increase to a greater extent. So this we call it as pole splitting is happening because of this compensation capacitor. Okay, let us have a look at okay, how does this zero comes into picture. How does this zero? Of course, now we got to know that because of this compensation capacitor, this omega p1 dash and omega p2 dash will move apart. So we got some intuitive proof into it. So let us see the introduction of this capacitor. How does a zero comes from infinity to a finite value? You can see actually zero was there at infinity, so zero has actually come to a finite value. Let us see the same lines how we just convinced ourselves, okay, this capacitance is no more C1, it will become this, and this resistance is no more R06, it is 1 over gm6. Let us see how does this zero comes into this transfer function. Okay, for that let us try to understand for an amplifier. Let us take a very general amplifier. Okay, let me just take, this is my amplifier. Just take it as some VDD, and you have some R load. This is output voltage, as in that this is M1. Let me take it as V1. Let me have two inputs for this particular circuit. This is V2. Let me say it as compensation capacitor, because some CC. You can see now I have an amplifier with M1, assume that biasing is always there. If you want to write, because there are actually two inputs, V1, V2, there are two inputs, you are supposed to find what is V0. So I can find V0. In first case, you make V2 equal to 0. So it is, let me write it as V01 plus V02. In this V01, let us assume that V2 is 0. Here let us assume that V1 is 0. So when V2 is 0, this is actually 0, you have short circuited this. So then what happens to the circuit? The circuit looks like this now. So since it is grounded, if you're writing the AC equivalent, this is RL, and this capacitance will come in parallel with this. This is actually CC. This is, let me write it as parasitic capacitance. Okay, and this is M1. Now it is V01. So what is V01 is equal to? Of course, it is nothing but this is V1. So can I write it as minus of V1 GM1 multiplied by the resistance offered by this. The resistance offered by this is the parallel combination of this and this. Can I write it as RL multiplied by 1 over SC divided by RL plus 1 over, of course this is SCC. So this is the output voltage because of this source. If you consider this source, neglect this source, then what is the circuit? How the circuit will look like? The circuit will look like this. So this is now 0. So you have, this is grounded, and you have a capacitor. There is a coupling of compensation capacitor. This is V2. This is 0 means, okay, it's like open circuit. You have this. This is RL. So what is V02 now? V02 due to Vin. So can you just think of this is like a potential divider. V02, I can write it as V2 multiplied by RL divided by the overall resistance. It's like a potential divider. You have this, and you have capacitor, and you have this. So this is your V02. This is RL. This is CC. This is V2. This is V2. Correct? So I can write the output voltage now is the drop across this divided by the overall resistance. It is RL plus S into 1 over CC. Now, do we have similar type of condition over here? See, now this is your output voltage. You have the inputs, one coming from this side, the other input is coming from this capacitor. Is it not similar to that of this exact condition where you have an input given to gate and there is one more input coming from the capacitor? See here, one input V0 dash is going to gate, V0 dash is going to this drain through this capacitor, which is exactly this. So I can write, okay, let me complete the expression for V0. So shall I now write V0 is equal to V2 RL by RL plus 1 over SCC minus of V1 GM1 RL into, of course, SCC divided by RL plus 1 over SCC is the expression. So now even though we have two different voltages V1 V2, if you come over here, the input for gate and input to this capacitor both are same. So I will write both V1 and V2 is equal to V0 dash. Instead of RL, what do you have RL here? So I can write what is, okay, let me just write it as, so what is RL now? RL is actually 1 over GM2. So CC we have it as it is. So why RL is equal to 1 over GM2? Because the resistance seen over here is actually 1 over GM2 in pair with R07, which is almost equal to 1 over GM2. Now, can I write this expression as V0 dash into, I will take out RL outside, is it not 1 minus GM1 was this, but actually for this circuit what we have, it is, this is actually GM2. I can write it as GM2 by S into CC divided by RL plus 1 over SCC. See now, so we are looking at what is the output voltage not by V naught dash. Just take out this. Just concentrate on this particular term. Is it not 1 minus GM2 by CC? Is it not a zero representation, this transfer function, which is 1 minus GM2 by CC? Is it not the same thing here? Okay, I can write it as so. This way we can able to get the transfer function for the representation of 0 can be, and this can be slightly of course, don't panic here. Okay, here we have it as SC into CC come in the denominator. We can slightly rearrange this term this way. We can take out this GM2 divided by S into CC common factor. It will end up with this over here. So finally you'll end up with the same term which is there in the, you can see this is the term what we have in this transfer function. You can see it is the same term what you have. So this way, this introduction of a compensation capacitor will going to actually bring a zero which is there at infinity to a finite value, that too on the right hand side of the S plane. So these are all the changes that will happen if we insert a compensation capacitor onto this circuit. So we'll see the impact of this compensation capacitor on the phase margin of the system in the next video.